Okay, so we're going to use these HF values that we were just talking about, and we're going to use them to figure out the energy of a reaction. So you're probably going to say, but HFs are a reaction and they already figured out the energy of their reaction. Well, kind of. Part of the reason we have HFs is because when we have elements and then they make one thing, some kind of a compound, so one thing, the elements are zero energy. And so when they measure it and they determine some amount of energy, that is going to imply that is just the energy associated with that one thing. So that HF is the energy of that one thing. So it turns out if you have each thing's energy for a different reaction, and again, these are from the HF values, you can figure out how much total heat energy is going to be produced from almost any reaction. So we have lists and lists of these HF values. And how the way you calculate it and turn it into basically the enthalpy of the reaction is you take the HF of the products and you add them together, that's summation, and then you subtract out the HF of the reactants all added together. So if you have like 2A goes to 2C, you really have a total of 2A. You have an A plus an A, and it's going to a C plus a C. And if the A has an HF value, if you've got two of them, they both have contributing HF values. So the HF values that we're going to be looking at today, we're going to do something with the coefficients to make it so that the entire quantity of the reaction is accounted for. So I've got a few tips on this. It's best to work these and just see some problem examples. So my first tip is when you write out this reaction, start here. Don't start on the left side. Start under the arrow. So H of reaction is equal to, and then we're going to put the side that's over here in that section minus the side that's over here. So I've got a few tips in here. The first thing I always tell people to do is look for the coefficients. This is 1, but I just go through and I put a little dot of 1 because that's how I know like I only need one of my HF values. Now I go through and I put in that this is negative 36.2. That the H plus happens to be 0, and that the bromine is negative 120.9. And so we're going to do products minus reactants. So 1 times 0, which is going to be 0, minus 120.9 minus negative 36.2. So hopefully you're seeing where this is all coming from. We'll do a quick little highlight here. So the 36.2 is coming from over here. And these numbers are going right there. So if you're tempted to write on the left, the only thing that sometimes happens is that when you start writing it out, even though you know it's products minus reactants, the first numbers you see when you look up are actually the reactants. And I've seen time and again, people will know that it's products minus reactants, and yet it still make the same error. So that's your H of reaction right there. We're just plug it in our calculator, which is no big deal at all. And then we'll get the answer. So negative 120.9, because the 0 is just 0, minus parentheses negative 36.2. So that gives us a total H of the reaction, or the enthalpy value, is equal to negative 84.7. And if you're wondering on the units, these come in a certain unit, but always check kilojoules per mole because each of the values are that value. So what this is saying is that heat is going to get released in this reaction because this already wants to give off energy. And then when you split it apart, you split it into other things that are even lower energy. They're willing to have a whole lot of extra energy. And so the difference in the two sides is going to be where the heat is. All right, now we'll go on to the next one. So now we have a few things in here. I'm going to go ahead and do what I was saying before. Put in the coefficients first. And then we're going to put in the values. Now over to the right, you can see these are the HF values. Looks like this is negative 1120.9. Looks like the aluminum one is negative 1669.8. Now, are there any other values over here? Most likely, that's because we're dealing with an element in the state that we find it in. So iron is definitely a solid, and that is an element. So it's automatically 0. We can look it up, but this is kind of like a common little question trick. And aluminum is an element and it's solid, so that's 0. So now we'll say H of reaction is equal to 4 times negative 1669.8 plus, basically it's 9 times 0. So that term doesn't really matter. Minus, parentheses, 8 times 0, again, that term doesn't matter, plus 3 times negative 1120.9. Then we say 4 times negative 1669.8, and that's plus 0, minus parentheses, 3 times negative 1120.9. And so my H of reaction is negative 3316.5. And notice that this is going to be in kilojoules per mole. And that's how you solve H of H reactions. For H of reactions, notice that this is exothermic.